Hi there, this is Professor Eckhouse, and I'm going to talk to you today about scientific notation. So we're going to start with talking about the tens. So 10 to the 0, as we learned with the exponent rules, just means 1. 10 to the 1 is 10. 10 to the 2 is 10 times 10, which is 100. 10 to the 3 is 10 times 10 times 10, which is 1,000. 10 to the 4, again, 10 times 10 times 10 times 10. You can put that in your calculator, see if you believe me, but that's going to be 10,000. 10 to the 6 is 1 million. 10 to the 9, 1 billion. And 10 to the 12, having to write smaller, is 1 trillion. Okay, so let's name these. This is a million. This is a billion. This is a trillion. It does get a little bit unwieldy though, doesn't it? So take a little moment here to look at the relationship between the exponent and the number of zeros. Exponent, number of zeros. It's the same. Okay, so when you're working with tens, powers of 10, the exponent is the number of zeros after the 1. All right, so if 1 billion is written like that, how could we write 2 billion? So 2 billion is, of course, 2 times 1 billion. But, writing all those zeros, why would we want to do that? So let's try doing it with scientific notation. And we are going to say 2 times 10 to the, what is a billion? It's 10 to the 9. Okay, so 2 billion is 2 with 9 zeros, or 2 times 1 billion, or 2 times 10 to the 9. So this is scientific notation. And it makes working with very large. Where would we use that? Well, when we're talking about like the number of atoms or cells or stars in the universe, or when we're talking about something very, very small. So, for instance, the size of an atom or the size of a cell or parts of a cell. All right, so it's used for very large or very small numbers, like I just said, atoms or the universe. So scientific notation, official definition here, is that a positive number is written in scientific notation if it is written as a times 10 to the n, where a is going to be between 1 and 10. Okay, between 1 and 10. It can't be equal to 10, though. So it's basically, a number between 1 and 9.9999999, right? And n, the thing we raise the power to, is an integer. So if n is negative, the power, it means it's a very small number. And if n is positive, it can be a very large number, generally larger than 10 at least. We don't usually use scientific notation for things less than 100. It's kind of a waste of time, but you can do it. So, and we will practice with it. So here's some examples of very large numbers and very small numbers. Okay, so here's our very large numbers. 500 is not that large, but you would write it as 5 times 100 or 5 times 10 to the 2. This would be 8 times 10,000. This one, 8 times 10,000, which is 8 times 10 to the 4, because 10,000 is 10 to the 4, and so on. So over here with the small numbers, 0.05 is 5 times 10 to the minus 2. 0.0008 is 8 times 10 to the minus 4. So why don't you stare at that for just a minute if you've never seen scientific notation and see if you can come up with a rule. Can you come up with a rule? So let's look at 43 million. So 4.3 times 10 to the 7, So if we said 4.3 was right here and went 1, 2, 3, 4, 5, 6, 7, the 7 represents the number of places we moved to move the decimal place to 4.3. And rather than memorizing the left-right thing, which you can do if you want to, just remember that when this number is positive, we're talking about a very large number. And when it's negative, we're talking about a very small number. So let's go look at a very small number. 0.0000 lots of zeros at 4, 3. So to get that to be 4.3, I would go 1, 2, 3, 4, 5, 6, 7. So there's a 7. It's a negative because it's a very tiny number, right? It's very tiny. It's less than 1. Okay, so that is the rule. That is the rule. The rule is that the decimal moves the number of places shown in the exponent. Okay, so a small number, a very tiny number, the exponent is negative. And a very large number, the exponent, and I'm just abbreviating because I'm running out of room, is positive. Okay? All right. So converting from decimal to scientific notation. So let's try these. Try to get back to a normal size here. Write the following numbers in scientific notation. All right, so give these a try on your own and then come back and see how you did. All right, so this is a very large number. So we're going to have times 10 to the and a positive exponent. So let's count how many places we would take to get to a number between 1 and 9.9999999, right? So we'd have to get to here, 9.2. Okay, so this is going to equal 9.2 times 10 to the something. All right, well, let's see what that something is. 1, 2, 3, 4, 5, 6, 7, 8. Now, it's 8. Now, 9.2 times 10 to the 8 is a huge number, and 9.2 times 10 to the negative 8 is a tiny number. This is a huge number, so we're going to leave it positive. All right, so you can also go and find the rule for positive and negative and which way it moves and memorize it, but I think it makes more sense to just know that a positive exponent represents a large number. All right, so we have another large number, 10,200,000. If you haven't tried it on your own yet, pause the video and give it a try. All right, so this only needs to have, the best way to think about this is there's going to be one digit with some other digits after it. So this is our number, 1.02. We do not use the rest of the zeros. Okay, so we get 1.02. All right, so how would we get there? 1, 2, 3, 4, 5, 6, 7. So times 10 to the, now is this going to be positive or negative 7? It's going to be a positive 7 because that is a large number. All right, the next one is 100 with a whole lot of zeros. All right, so where's the decimal going to go? Well, you want one digit and then a decimal point. So it's just going to be 1, because we're not going to put 0.000. What's the point of doing this if you're still going to write all the zeros? So part of the point of this is not have to write all of these massive amounts of zeros. So if you're in chemistry, you know that there are 6.02 times 10 to the 23rd atoms in a mole, right? Who wants to write 23 numbers, right? So we're just going to say times 10 to the 23. All right, so back to this. So we've got a decimal, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So times 10 to the 11, is it going to be positive or negative 11? And it's positive because that's a huge number. All right, so those are big numbers. Now let's look at some small numbers. I'm not going to rewrite these. We're just going to write it right here. How's that? All right, I'm going to make it big. All right, so, oh my goodness, we need to get all the way over to right there. So this is going to be 3.5 times 10 to the negative something. Negative because it's tiny. Okay, so let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Negative 12. 3.5 times 10 to the negative 12 is that number right there. You try the rest and then come back and see if you get them right. All right, the next one, 102 is my number. So I want to put the decimal there. So I only have one digit. So my number needs to be between 1 and 9.9999. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. So 1.02 times 10 to the, I just counted backwards, 8. So it's because it was a tiny number, so it's a negative. So again, a lot of people just memorize the right and left, but I think it's confusing for people. I've seen it really confuse a lot of people because it depends on what you're doing. Are you converting from scientific to decimal or decimal to scientific? And then you have to memorize which is which. And So just remember negative number, tiny number. Okay, so this is going to be 7.93. 7.93 times 10 to the negative something, because that is a very tiny number. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Negative 15. I got a little googly-eyed, so let me look at my, negative 15. All right, so that's how you do those. Okay, let's move on to converting going in the other direction. And this is supposed to be up in the, there was a typo. I don't know how that happened, but convert from scientific to decimal notation. So I'm going to rewrite this. 4.8 times 10 to the minus 4. So that minus 4 is supposed to be up there. Okay, so here's how I would do these. You know that this is going to be a tiny number, right? So is the decimal going to move left or right? Because this says tiny number. Tiny number. So it is going to go to the left to make a tiny number. If you went right, you'd have a huge number. All right, so let's start with the number out here by itself. And I'm going to go to the left 4 places. So 1, 2, 3, 4. There's my new decimal point, like that. So I get 0.000. Let's rewrite it to be a little neater. 00048. That's my original number. All right, let's try the next one. 3.08 times 10 to the 6. So big number, small number. So hopefully you see it's going to be a large number. So large number, definitely bigger than 3.08. All right, so let's write 3.08, and I'm going to have to count, and I'm going to go to the right to make the number bigger. So 1, 2, 3, 4, 5, 6. There's my new one. Be careful with your bubbles so that you get a 0 in each one. And I'm going to have 308 and then 4 more zeros, and then you can go back and put your commas in. So 3,080,000. Okay, so that is going from scientific to decimal notation. All right, so now we're going to look at multiplying and dividing numbers in scientific notation. And you can use associative and commutative properties to comply in like terms. When we are in class, I can show you how to use the scientific notation button on your calculator. But right now, I really want to show you how we can use all the rules that we know to rearrange this. Okay, so I'm going to take the 3 and the 6.8, because this is all multiplied. 3 times 10 to the 8 times 6.8 times 10 to the minus 13. So you can rearrange it using associative and commutative properties. So 3 times 6.8 times 10 to the 8 times 10 to the minus 13. So now these two have the same base, and we can use the exponent rules. These two we can just multiply easily on our calculator, and this is going to give me 20.4, and this is going to give me, so times, or I'll write times, 10 to the 8 plus negative 13. Okay, so 20.4 times 10 to the negative 5. All right, so now what are you going to do with that? So 20.4 equals 2.04 times 10 to the 1. And then that's times 10 to the minus 5, because we've got to bring this down. All right, so now we've got 2.04 times 10 to the 1 times 10 to the minus 5. 2.04 times 1 plus negative 5 is negative 4. 2.04 times 10 to the negative 4 is the answer. Doing this kind of the long way, but just wanting you to understand that you can take these things apart and rearrange and do what you need to do to solve them. All right, I'm going to show you one with 3 different numbers. So here we're going to take the 8.2, the 1.5, and the 1.9. 8.2 times 1.5 times 1.9. And then I'm going to go like that and say, no, those are going to go together. Times, now we're going to do the 10 to the 6, the 10 to the minus 3, and the 10 to the minus 7. 10 to the 6 times 10 to the negative 3 times 10 to the minus 7. All right, so the 8.2 plus 1.5 plus 1.9 in the calculator is 23.37. And that's going to be times 10 to the 6. So we've got 6 minus 3 minus 7. Be careful. and that is going to be 6 minus 3 is 3, minus 7 is negative 4. All right, so I get times 10 to the negative 4. All right, but remember that this is not a number yet between 1 and 9.999. So we're going to have to change that to 2.337 times 10 to the 1, and that is times 10 to the minus 4. So now we've got 2.337 times 10 to the 1 plus negative 4 is 10 to the negative 3. Okay, so that's the final answer. All right, next one, dividing. So division is very similar. We can say we're going to divide these two and multiply it times that. Okay, so you can rearrange multiplication. There's no addition in here, so you can rearrange and do things in any order. So 2.829 divided by 3.45 is 0.82. And then we've got times, and then we've got 10 to the negative 9 minus negative 3, because they're divided. All right, so that is 10 to the negative 9 plus 3, so that is 10 to the negative 6. 10 to the negative 6. All right, but 0.82 is not between 1 and 9.99, so I've got to turn this into 8.2 times 10 to the minus 1. And that is times 10 to the minus 6. So this whole thing becomes 8.2 times 10 to the minus 7. Again, the long way, we'll find the button on the calculator so I can show you how to do that. All right, so this one, again, I would just do this on the calculator, but I'm going to show you the long way because I can't display my calculator very easily. So I'm going to just show you how to do it. So I'm going to do basically 1.37 times 9.85 divided by 5. So 1.37 times 9.85 divided by 5, or 5.0, right? And then that's going to be times 10 to the 4 times 10 to the 6 over 10 to the 12. Now again, if there were any pluses in here, this would not work. I just rearranged the top, right? Rearranged the bottom and then kind of pulled them apart into the pink and the green. All right, so in the pink, I get 2.6989. And in the green, we might need to do a little work here. So we've got 10 to the 4 plus 6, that's the top. And now we can do this all in one step and say minus 12. 4 plus 6 is the top, and then we subtract the bottom, so that's the product rule and the quotient rule combined together. If you're not good at that yet, practice. 10 minus 12 is 10 to the minus 2. So I get times 10 to the minus 2. And that's my final answer. All right, so from here we have some application problems. So we're going to look at, why don't you pause the video and read through this problem right here. All right, so human cells come in a wide variety of shapes and sizes. The mass of an average human cell, we've got a number here, so I'm going to say mass right there, grams. Red blood cells are one of the smallest types, clocking in at approximately 10 to the minus 6 meters cubed. Okay, so that is a volume, so it's cubed. So usually I would write meters cubed as m cubed. I just think it's a little weird to put a cubed on a word, but meters cubed. Biologists have recently discovered how to use the density of some types of cells to indicate the presence of things like sickle cell anemia and leukemia. So remember the density, so this is important right here. They're giving you a formula without writing it as a formula. Now we're supposed to calculate the density. So let's just write that as a formula. So density equals mass over volume. Okay, so let's go I'm going to go write down what everything is. Mass is in grams, not in meters cubed, so use the units to figure out what's what. 2 times 10 to the minus 11 grams, and volume is 10 to the minus 6 meters cubed. Okay, so the density over here is going to be the mass, 2 times 10 to the minus 11 grams over 10 to the minus 6 meters cubed. So this is going to be in grams per meters cubed, and that's fine. That's a density measurement. And we get, so these two can be combined, minus 11 and minus 6. Okay, so we're going to have 2 times 10 to the minus 11 minus negative 6. Okay, I'm using the exponent rules. And that gives me 2 times 10 to the negative 11 plus 6 is negative 5 grams per meter cubed. Okay, so 2 times 10 to the minus 5 grams per meter cubed is the density of an average human cell. We're talking about red blood cells. All right, so that's one example of using this. That's a tiny example. This is a huge example. So this one is about the speed of light. And one thing that you need to remember before we begin is that velocity equals distance per time, right? Like miles per hour, distance per time. So you can rearrange this to use it in different ways. Okay, so it depends on what you're looking for. So here we've got the speed of light. All right, so let's write that down. Is that velocity, distance, or time? So make sure you label everything. Velocity equals, because that's the speed, right? Velocity is speed, 3 times 10 to the 8 meters per second. All right, the next one, if the sun is 1.5 times 10 to the 11 meters from Earth, so what is that? We've got velocity. Is that distance or is that time? So make sure you're thinking about these things. So this is distance and this is velocity. So our distance is 1.5 times 10 to the 11 meters. Please do not skip this. Don't skip. Don't skip this. This is really key to the people who are more successful at these kind of problems and don't make as many mistakes, because you have everything all lined up when you're in a physics class, a chemistry class, applied problems class, and math class. Just really important. So, all right, so how many seconds? What is that? Well, that's t. That means t is what we're looking for. So I'm going to come down here and say t equals question mark. All right, so our original equation was v equals d over t. All right, so we need to solve for t. We need to know what t is. So I'm going to multiply both sides by t, and I get vt equals d. Now I need to divide by v, and I get t equals d over v. Okay, so now we can solve. All right, so now I'm going to plug in my distance, which is 1.5 times 10 to the 11 meters over my velocity, which is 3 times 10 to the 8 meters per second. And the meters are going to cancel out, and I get per second, so seconds come to the top. But just look at the units and think, well, what is time going to be? If we've got seconds in one of them, it's going to be seconds. All right, so we've got time equals 1.5 divided by 3 times 10 to the 11 divided by 10 to the 8. 1.5 divided by 3 is 0.5 times 10 to the 3. 10 to the, well, let me not take a shortcut there. We've got 11 minus 8. All right, so that is 0.5 times 10 to the 3. So that's not in scientific notation. So remember, we've got to rewrite this one as 5 times 10 to the minus 1 times 10 to the 3 equals 5 times 10 to the 2. Well, what is that? That's 500. You could also write it as 500. So 500 seconds. All right, it takes 500 seconds for sunlight to reach the Earth. So make sure you get to the end and go back to the problem, make sure it makes sense. 500 seconds. All right, that is the end of this talk. Thank you for watching.